Here's your first look into Chapter 8, dealing with exponential growth and exponential decay, these first two sections here. So first, let's talk about this exponential growth model. Here is the exact formula for exponential growth. It is a times b to the x power. The last couple chapters, if you remember correctly, we've been doing like x squared, y to the 1/2, where these have all been numbers, where now we're going to start putting x's up there instead of just numbers. So, let's talk about what each of these letters mean. This letter y out here, this is your ending amount. This is how much you end up with when you have an exponential decay, or excuse me, an exponential growth problem. This letter a here, this is your starting amount. It's how much you start with, whether it would be dollars or cells of bacteria or something like that. This letter b is what we call the growth factor. And this letter x is also what we call, this is going to be our time. Yeah, sorry about that. This last x here, this is your time. So, knowing all of those, let's look at an example. Here's an example of what an exponential model equation looks like, where here, this is your ending amount, this right here is your starting amount, this would be your growth factor, and there's your time. So knowing all of that, it says, what was the average professional baseball player's salary in the year 1998? Well, it says that this is starting in 1984, and I want to know 1988. So what I'm going to do is in my y equals equation here, I now know what the starting value was, which is 283. My growth factor is 1.2. I now know my time. You subtract these two, I want to plug in 4 years, and that will give me my ending amount. So let's talk about how to plug this into a calculator. So let's go to our calculator here. Rather than try to punch this in all as one expression, what I'm going to do is I'm going to split this up and show you how you can use the enter button and how your calculator will store some of these numbers for you, so you don't have to sit there and try to put in parentheses and making sure this exponent goes with this parenthesis and not this one. It gets a little bit confusing. So here's what we're going to punch into our calculator. I'm going to go this 1.2, and I'm going to take that to the fourth first and push enter. So I'm going to go 1.2 to the fourth, enter, and then times 283. And you should get 586.828. 586.828. If you round, or this is talking about in thousands of dollars, so if they want to know what the salary is, thousands is 3 places, so you go 1, 2, 3. So technically, each player made, on average, around $586,828 on average. For the current year, it is currently 2011 right now. So if you wanted to plug that in for 1984, you would have to plug in a lot of years. If you subtract those two, you're going to have to plug in 37 years. Or 37. Let's try 27. You're going to have to try to plug in 27 into this exponential model. If you do that, what you're going to find really quickly is your numbers are going to get blown way out of proportion. If you go 1.2 to the 27th power, enter, times 283, you'll find out that the average baseball salary, according to this model, would be around $38 million. Is it 38 or is it 3? I think it's 38. Yeah, it's 38. 38,875. 0.866 or whatever it happens to be. So it would be about $38 million. And obviously that is way too much money. Baseball players, they do make a lot. If you want to see how much baseball players do make, you can go log on to ESPN.com and go to Salary Crunch. It'll show you how much some of those people make. But this is way too much money. So the answer is, would this model still be accurate for the current year? The answer is no. So when a real-life quantity increases by a fixed percent, meaning this percentage up here, this 1.2, is constantly going to be changing because, as you know, baseball players have a union, and they're always trying to negotiate different deals, different contracts, so that rate is going to change. But if we do have a fixed percent, or a percent that we know for a certain time period, we can rewrite this model so it looks a little bit different, but it's still technically the same. We're going to go A, which is again your starting amount, parenthesis 1 plus R, parenthesis to the t power. Where this again is your starting amount, this here, this is your percent that you're increasing, except you have to remember that this percent needs to be written as a decimal. And then this exponent out here is again your time. Where does this come in handy is if you remember in class, or if you were gone for class, we talked a lot about savings accounts, stocks and bonds, mutual funds. People use this kind of information all the time when trying to figure out how much money you're going to have in the long run. In example 1 above, by what percent is the average baseball salary increasing each year? So if I wanted to know the percentage here, that's this little letter R. This is my percentage. I suppose I can highlight this for you. This is my percentage right here. If I want to know what the percentage is up above on this example 1, I'm just going to ask myself the question, okay, how far is this 1.2? How far is that away from 1? Because I know I got to go 1 plus that. So 1 plus that rate equals 1.2. You subtract 1 from both sides, you'll get 0.2. Move the decimal place twice, and you'll find out that it's increasing 20% each year up here. So this would be a fixed percent example, but we're going to create our own down below here. So knowing that, here's another good statistic for all of you out there dealing with college. Because if you didn't know this, college actually will cost more when you're done than when you started, because it does, the price of college goes up about 4% each year. Some colleges go a little bit more than 4. If there's a good year, maybe they'll go a little bit less, but you can expect to get right around about 4% each year as an increase. So let's write a model that gives the tuition in dollars T years after 1990. So we know the starting cost was $4,300, so I'm going to go Y equals. My starting cost, $4,300. Parenthesis. I'm going to go 1 plus, this is my percentage, but I have to get that as a decimal first, so I got to go 0.04 to the T power, because it wants to know after T years. This would be the model, and I'm going to simplify just a little bit. Going to combine those things in the parentheses, so I get 1.04 to the T. This would be the model that would tell you, based on the school's current rate of increase, how much you could expect in 2010, how much you can expect to pay. So what I'm going to do there, in 2010, that would be 20 years after 1990. So I'm going to go 4,300, 1.04, that's 20 years. I'm going to go back to my calculator here, making sure that I plug in 1.04 to the 20th first, then push enter, then times 4,300. And at the current rate of increase, you can expect to pay about $9,421 in tuition 20 years later. That is using exponential growth. There is one other way that we are going to use exponential growth, and it has to deal with, if you flip over to page 2 in your notes, it has to do with compound interest. This is actually going to be the exact same formula as it was over here, and I will circle it. It's going to be this exact same formula, except we compound the interest, which means we take it more than just once a year. All the rest of those problems we're saying, okay, if you take the interest once a year, how much do you have? But we could also take the interest, sometimes they call it biannually, which would be twice. They may say quarterly, which means you do it 4 times a year. They may say monthly, they may say weekly, daily, whatever. So they might do it more than once a year. Same formula. We're going to go A equals, it's your starting value, which is, they call it principal for P, parenthesis, 1 plus your rate, but instead of just having your rate here, you have to divide by n, and if you divide by n out here, we're also going to times by n in the power out here. What is this n? This n is simply how many times do you do it per year. So if it's biannually, your n would be 2. If it was quarterly, your n would be 4. If it was weekly, since there are 52 weeks in a year, it would be 52. So the A is your end amount again. This always equals your end amount. Your P is how much you started with. They call it principal, but I'm going to call it start amount. Your R is the same thing as it was in the previous problems. It's your rate as the decimal. The only new thing we're throwing in here is we now have an N down here and an N up here, where this N stands for how many times a year is it happening? How many times per year? And your T again is how many, the time involved in this. So let me show you an example. Actually, we're going to do 3 examples all in the same one. We're going to go annually, semi-annually, and quarterly, dealing with $1,500. Okay, so first let's take care of annually. Annually means once a year. So I'm going to go back above and I'm going to use my formula. Y equals A, well, this is your starting value. I guess up above they called it P, but we're just going to call it your starting value, which is 1,500, times 1 plus, your percentage as a decimal is 0.06, over N, which is how many times you do it per year, or if it's annually, it's once a year, to the, they want after 2 years, and you're, again, annually is once a year, so you go 2 times 1. So we go 1,500 times 1.06 squared. Where if you grab your calculator and do that, you should get right around 1685.4. $1,685.40. Compounded annually. Semi-annually, let me get a different color here. Semi-annually means twice a year. So I'm going to use this exact same formula, y equals 1,500, because that's my starting value, 1 plus 0.06. Instead of dividing by 1, when it's semi-annually, I have to divide by 2. And because I divided by 2 out here, I got to multiply by 2 out here. So you end up with 1,500 times, divide these and add them, you'll get 1.03 to the 4th power. Again, grabbing your calculator and punching that in, you should get right around $1,688.26. So you get a little bit more money if it's compounded semi-annually. And the last one we're going to take a look at, switching back to red here, we're going to take a look back at our quarterly using the exact same formula, except quarterly means 4 times a year. So I'm going to go y equals 1,500, which is my starting value, parenthesis 1 plus 0.06, divided by, quarterly is 4, and if I have a divide by 4 here, I have to have a times by 4 up here. So we end up with 1,500 times 1.015 to the 8th power, which again, grabbing your calculator to check, will give you $1,689.73. So slight difference. This is used in banking and marketing and so on quite a bit. So the key thing to remember here, it's the exact same formula as it was before. The only difference now is these 2 green highlighted things, which are N and N. You have to divide by how many times you're doing it per year and also multiply that up here. Okay, flipping over to page 3. Last thing we're going to talk about in this video is we're going to talk about exponential decay. Same formula. A, B to the x. Same thing here, where your y is your end amount, your a is your starting amount, your b, instead of growth factor, this is now going to be a decay factor, and your x is still your time. The one thing to note is right here, this is the big key difference, is b is between 0 and 1, where back here, b was greater than 1. That means here it's going to be like 1.2, 1.85, 2.3, something like this. It's going to be bigger than 1. Where when we start doing decay, it's got to be less than 1 but bigger than 0, meaning it's going to be some sort of decimal, like 0.85, 0.76, 0.98, 0.99. These are all examples of decay. So, right here, this is a great application of exponential decay. Talking about pharmacy and the concentration of a stomach medication or any kind of medication in a person's bloodstream. It can be written as this equation right here. How much medication remains in the bloodstream after 2 hours? That just simply means we're going to take our formula, and now I know how much time they want to put in. They want to go 2 hours. Plug this into a calculator, and you should end up getting 307.37 milligrams or milliliters or nanogram. What is it? Nanograms per milliliter after 2 hours. Same concept as before. This, if it has a fixed percent, meaning the percent doesn't change over time, then we're going to write this as the exact same thing as growth, where it's A, parenthesis 1. The only difference now is instead, because we are decaying, we have to subtract an R, take it to the t power. Otherwise, it's the exact same formula as it was. If I go back here, right here. This exact same formula, the only thing I'm changing though is instead of plus, I've got a minus. So using that, in example 1 up above here, if you wanted to know what percentage this 0.79 was, you would say, okay, I know that 1 minus that 0.79 is going to equal this R. I know that 1 minus my rate here, which is 0.79, is going to equal this. So 1 minus 0.79 is 0.21, which is 21%. Meaning, if you have 0.79 as a decay factor, because that is 21.21 away from 1, therefore you have a 21% decrease. Last 3 examples we're going to go over together, and then I'm going to, and then you're going to have an assignment over this. I guess there are no examples in the packet. So let's talk about whether something is exponential growth or exponential decay. This first one, to figure out if something is growth or decay, remember the only difference between the two was this concept. If it's less than 1, it's decay. If it's greater than 1, like these, it's going to be growth. So the only thing I'm concerned about is my growth or decay factor right here, and right here. Because 2 over 3 is less than 1, this is decay. Because 3 over 2 is 1.5, that's bigger than 1, this is growth. And because 3 is bigger, but wait, there's one small catch here, negative power. If you've watched any of the Chapter 7 videos, you know that a negative power means you need to flip it and make it positive. So instead of 3, it's 1 over 3, and since this is less than 1, that letter C is a decay. So watch for those negative powers. That should hit us up for growth and decay. The big thing to remember, and I'll write it on a whole new slide here, is this. Y equals A, parenthesis, 1 plus or minus R to the T. This formula is used for both grow and decay. The only thing that changes would be the sign right there.